Hello and good afternoon, everyone, and welcome to another session of Asset Volume Talk here. Today, we are privileged to have Ayushi Mukherjee. She is currently pursuing her PhD in Nanoelectronics Lab with Professor Mandar Deshmukh and in our DCMPA MS section here in TFR. Before joining TFR in 2020, she earned her bachelor's in physics from St. Xavier's in Kolkata. In the nanoelectronics lab, she primarily focuses on studying superconductors in twisted graphene systems and aims to understand how such exotic phases emerge in this material, superconductivity. In addition to her research, she is also very keen on propagating and participating in outreach for science, education, and activities at TFR, and also in a gender advocacy in STEM. She's been touring various courses at Vigyan Vidushi in physics and other things here. And if I remember correct, she was also part of a 2020 Vigyan Vidushi herself, doing that. So without any further ado, I request for
hello, everyone. I hope you can hear me all right. So today I'm going to be talking to you about my work based on this magic angle twisted trilayer graphene and how we found that it is an inhomogeneous twisted superconductor that shows magnetic order. So the plan of the talk is I'm going to tell you a little bit about why twistronics is interesting in the sense that why do we like to twist these materials and essentially make our lives a bit difficult, but then there are interesting things that we see which kind of make it worth it. Then I'm going to be talking about the superconductivity that we see essentially in this MATTG, which is magic angle twisted trilayer graphene, and a little bit info about how do we go about making such devices, and then how do we measure these devices, which is the switching technique. And at the end, I'm going to tell you about a BKT transition and superfluid stiffness estimate that we did in our work and summarize and end the talk. So going ahead, yeah. So basically, all that I'm going to be describing to you has been published in this paper in Nature Materials. So you can find more details about the work here. So twistronics, basically, what do I mean by twistronics? So we know that monolayer graphene is a single sheet of carbon atoms. And if I look at the lattice, these are like each carbon atoms, each point is a carbon atom, and they are basically in a hexagonal lattice space. Now, why is graphene also interesting is because you can tune its Fermi level by application of some gate voltages or electrostatic voltages to graphene. What appears is that this is the band structure of graphene, which is basically a linear dispersion of Dirac curve, we call it. And if we apply some electrostatic voltages to graphene, what we are able to do is we are able to tune the Fermi level of this system. And actually, when we study all of the electronics, what we are actually probing is the physics quite close to the Fermi level. And in a sense, then we are able to actually study the entire band structure in a single system. Secondly, these monolayer of graphenes then can be stacked one on the top of each other. And here comes the interesting part, the twist, is when we actually literally twist these materials and stack them. They form this nice moire pattern that you can see. And this moire pattern actually adds an additional periodicity to these systems. So the inherent periodicity in the system is obviously the lattice periodicity, which is why you have a crystalline lattice structure. But when I twist and I put these materials on top of each other, you can see this emergence of this pattern, which is another form of periodic length scale, which is larger than the lattice length scale. And that brings about interesting physics in the system. Now, depending on the angle of twist, actually, the system's band structure can vary a lot. So what these diagrams are different band structures for different twist angles of the twisted trilayer graphene. Now, if you notice closely, these red bands, close to this 1.5 and 1.6, these red bands are quite flat. They're literally called the flat bands. And that gives us a stage for studying strong electron correlation, because if I have these flat bands, what that essentially means is that the kinetic energy in these bands is suppressed. The only way then, the only dominating part in the Hamiltonian that remains is electron-electron correlations. And this then sets the stage for me to probe that electron correlation without having to worry about the effects of large kinetic energy. So that's why basically twistronics is interesting, in the sense that I can change the properties of a material just by changing what angle I dial between these materials to stack them. So that is basically twistronics. Yeah. So not only twisted trilayer graphene, what I'm going to be talking about today, but there exists actually a family of this alternate twist angle superconductors. Alternate twist meaning I can always stack two layers with theta. Now I have a choice whether I want to stack the third layer as theta, or I can go and do it as a minus theta. So while I'm doing the successive layers of stacking, I can go about going theta minus theta. That's what I mean by alternate twist angles. And not only 3 layers, even 2, 3, and 4 layers, and even 5 layers of this alternate twisting stacking of graphene actually gives rise to this flat bands. And not only that, they also show this superconducting phase. So in a sense, whatever I'm going to be describing is particular to magic angle twisted trilayer graphene, but we are hopeful that more studies can actually relate these superconductors to a larger phenomena that's occurring in this family rather than a particular individual system. So superconductivity in twisted trilayer graphene, what are its essential nice properties? So obviously it's a part of this multi-layer twisted graphene superconductors. This is 3 layers of graphene. And like I told you, it hosts the Dirac band, which is a reminiscent of a monolayer band structure, but also these flat bands, which is actually the essence for strong electron correlations, and is thought to be the ingredient which causes the emergence of superconductivity in these materials. Thereafter, there is this nice thing called Pauli limit violation. Now, superconductors in general do not like magnetic field, and that is a general perception that we have. Whenever we apply some kind of magnetic field to a superconductor, it tries to go out of that superconducting phase. Now, when I apply some in-plane magnetic field, now these are basically 2D materials, as you can understand. You can apply in-plane or out-of-plane magnetic field. There is some sort of notion from previously known superconductors and theories, which is the celebrated BCS theory of superconductivity, that, okay, if I apply a certain amount of in-plane magnetic field, my superconductor should then turn into a normal state. How that happens is essentially vanilla-like superconductors are thought to be spin singlets, which is one spin up and one spin down, forming a Cooper pair. But if I apply some in-plane magnetic field after a particular magnetic field, there should be Zeeman splitting, thereby breaking this Cooper pair. And at that point, I should not see the existence of the superconductivity anymore. So there is some theoretical estimation for that, and that is known as the Pauli limit in a superconductor. Now, this MATTG is an unconventional superconductor, which means that it does not follow all the rules of the BCS theory. When I try to estimate this Pauli limit with BCS theory, it should appear something like 3 Tesla of magnetic field, after which it should not show any superconductivity. But as you can see from this plot, the zero resistance, which is the blue part, it sort of survives up to really large magnetic fields of 9 and 10 Tesla, which tells us that there is something different happening in this kind of superconductor, and you cannot really fully explain this in terms of BCS theory. Not only that, MATTG and other graphene systems, like I said, you can tune their Fermi levels with some gate voltages. And when you do that, you not only encounter the superconducting phase, but other multiple phases that live right in that phase diagram just on the side. So there are these semi-metals, insulators. There are also theoretical predictions of when a superconductor Cooper pair can be a singlet or a triplet or a combination of these two. So in a sense, it's like a stage offering you a variety of phases in the same system that you can probe. Yes. Yes. Right. So what happens is that what we are tracking in this graph is basically the resistance. So in a sense, zero resistance means a superconductor. Now that superconductor to normal state, where it's not a zero resistance, is not particularly sharp in these systems. So you can, in a sense, give it a definition that, okay, when my resistance is 10% of the normal state resistance, I will consider it to have transitioned versus 20 or 30. That's subjective.
That's like the threshold.
Yes. Yes. Just to get an idea of what the transition, so in the temperature axis, it will be the transition temperature, the critical temperature. So just if you want to get an idea, you can sort of define that, okay, I'm going to consider 10% of normal resistance to be the transition or the critical temperature. Yes, so you can understand from this color scale that the orange part is like 5 kilo ohms in resistance. Yes, so it's completely normal at that point. Okay. Yeah, so basically, not only do I have these multiple phases in my MATTG, the superconductor itself is tunable with these electrostatic gate voltages. So this is again a resistance map with doping and electric field that I can apply to these systems. Now, the blue parts are the superconducting pockets where you have zero resistance, and the other parts are insulators or other kind of metallic regions. Now, I want you to focus that there are two pockets, and if I take these two pockets to plot how my critical temperature changes with the doping, I can actually get different kinds of superconductor with different critical temperatures depending on the doping. So in a sense, not only do I have two superconducting pockets, I can tune them to get to any critical temperature point, in a sense that these superconductors are then tunable and not only some one phase that we are getting. Yeah. So the next I want to sort of describe how do we make these devices in our lab. So the first step is to actually get the graphene that we want to work with, the flakes, and that's the main ingredient of our devices. So what we start with is like a mechanical exfoliation. We take a tape, which is known as a Scotch tape, and we take some amount of bulk graphite crystal on it. Now, the process of mechanical exfoliation is that I stick this tape on top of it and then peel it again. And in doing so, I make multiple copies of that crystal on the tape. So I essentially have a density of that crystal on the tape, and a real life picture sort of looks like this. And then I can transfer this to another daughter tape, and then essentially finally to a silicon substrate where I am able to visualize these graphene monolayers, bilayers, or some other flakes and work with them. So this is an optical image of how a monolayer of graphene looks like. If you see the scale bar, it's like 30 microns. So it's essential that I use a microscope because I will not be able to see this with my naked eye. And this is another cousin of graphene, which is what we call a boron nitride. And oftentimes we like to encapsulate our devices between two flakes of boron nitride. So Once I have identified a monolayer of graphene, now I need to make 3 pieces of this, because ultimately I want to make something that is stacked over 3 layers. So how do I do that? And essentially I cut this graphene. Yeah, that's a good question. Actually, what we use a substrate, the silicon on silicon, so basically it's a substrate of silicon oxide on silicon. That is a specific length, thickness of silicon oxide that allows me to identify different layers of graphene depending on the contrast. So you can see that this is a monolayer of graphene. If I would have something that is a bilayer, it would be a higher contrast. So depending on that contrast, I am able to identify. And the contrast appears because of the special thickness, which is basically an optical interference that is happening from the SiO2.
And you also calibrate that by Raman.
Yes.
Whether it's the cross check against the optical one.
Yeah, so we calibrate what contrast we are getting with Raman to sort of make sure that what we are getting is a monolayer. Yeah, so then basically we take something that is like a fiber optic scalpel and literally cut this monolayer graphene into 3. So this particular flake, if you can see, I don't know if the contrast is really good, but there is a cut here and here. So basically, I have separated one monolayer into 3 layers that I can stack. Later on, we also figured out that this same thing is much easily done using a laser cutting setup wherein I focus some high energy laser just to ablate the graphene in between. And I do that with the help of this microscope and laser fiber. And basically, then I get cleaner cuts because I'm not mechanically, literally scratching the graphene. Some milliwatt, tens of milliwatts. Focused, yes. So we couple the laser fiber to the microscope and then focus it. Otherwise, if I go unfocused, I would sort of burn anything and everything on it. Yes.
The fast speed. Or in this case, it's a fast speed.
Yeah, so once I have these 3 layers, now I have this, I have the task at my hand to actually make the stack. So how I do is with the help of this sticky polymer-like substance, which is like a PDMS, we call it, and it essentially acts like a stamp. Whenever I touch the graphene, it picks it up. And so basically, then I go in with this PDMS and then pick up each layer successively on this stamp and make this stack. Now, while I am doing that, I have to take care that since this is a twisted stack, I need to apply the relative angle between. So basically in intermediate stages, I am rotating the graphene so that I get the twisted sort of structure inside. Yeah, so basically, you can understand that these are micron level flakes. And if I try to do anything with my hand, it will be imprecise. So, and in my previous slide, you can see that if I go from 1.5 to 1.7, I don't get as flat a band and I will not get superconductivity. So it's essential that I hit that precise angle. So there are basically ways to get around that. So manually, how we do it is we use a screw gauge to sort of fine tune it and do it. And now there exists also these high precision piezoelectric or motorized stages where you can sort of not worry about your precision of the hand and sort of dial in a number and get that done. In this 5 years of my stay in TIFR, we have, in the last year, we got a motorized stage, but previous to that, we have been doing it by hand. Yeah. So yeah, so now basically I have a stack ready, which basically is this blue thing inside in this picture, but now I want to sort of measure the electronics, so I need to make electrodes to that. So there is a post-stacking process of lithography and evaporation of metals where I make actually contacts, and the final device sort of looks like this. And the motivation for this geometry, this is a Hall bar geometry, which basically allows me to not only measure resistances in the direction of the current, but also in a perpendicular direction. So I am able to get linear as well as transverse resistances and infer different physics from that. So essentially Hall bar, because I'm able to get transverse resistances, which is the Hall voltage.
How long does it take on the day you start for the challenge of
finally?
number 6?
Yeah, around conservatively speaking, 2 weeks. Yeah, from the moment I get a flake to the final device. Getting the flake itself can also be challenging because that depends on luck and also the stochasticity of whether you're getting a monolayer flake large enough to cut into 3 pieces. That requires a certain amount of skill as well. So once those things are overcome, this can be done in 2 weeks. And okay, I will come to that part later. Yeah, so in our work, when we have a device ready, the next step is to measure it. So we usually cool it down to millikelvin of temperatures, and we do a similar plot where basically we are mapping the resistance of the device as a function of doping and electric field. Now, similar to what a plot that I showed you before, I also see zero resistance in 2 pockets of the devices. And if I try to sort of do DC measurements, DC IV measurements to characterize these superconductors, so the blue curve is for the whole side doped of the superconductor. So the superconductor basically shows a 0 voltage drop till a point where it crosses to a non-zero voltage after this current, which is the critical current of a superconductor. Now, for the electron side, which is this green curve, you can see that it sort of switches from the 0 voltage to a non-zero voltage at a much lower current. So in a sense, the electron side superconductor is much weaker than the hole side superconductor. So we get 2 types of superconducting pockets in the system which are having distinct character. They are not the same phase. And not only that, if I even within this pocket change the doping, I will get slightly different kinds of critical current and TC that will of the superconductor itself. So in the next plot, what I will show you is basically a 2D visualization of this curve. And what happens to this when I go along this axis is when I change the electric field. So this is the hole side superconductor and this is the electron side superconductor. White basically means that there is a 0 voltage drop and it's still in the superconducting part. Red means positive voltage drop and blue negative. So it's transitioned into a normal state. So even with the y-axis, which is that the electric field that I'm applying to the system is changing, the superconductor changes its behavior and the critical current changes. And you can see that between the hole side superconductor and the electron side superconductor, the behavior with the electric field is remarkably different. Yes. Yes. Good question. Yes. Yes. Okay. Yeah. I mean, one brute force way to know is whether I have got the superconducting phase. If I am way off in angle, I will never get the superconducting phase. But even yes, yes. Yes. So even the superconductivity is not fixed to a particular angle. There is a small range of angles wherein I can get the superconductivity. Now, how do I know what angle is this? Why have I written 1.56 degree? So what happens is that, like I told you, with angle, the band structure changes, right? And when the band structure changes, the level spacing between the bands change. So in a sense, the amount of doping I need to cover up a band changes. So when I enter this red part of the phase diagram, it tells me that I have entered a high resistance state and there is no density of state. So I have crossed a band. And this basically the amount of doping that it took me to cross a band is related to the twist angle in the system. So that's how I can infer that this particular system is this angle.
You can also compare.
That's right.
So how do you know that you are not getting this superconductivity from useless error?
Okay. In a sense, the two-layer superconductivity, the angle range at which you need to hit to get that two-layer to be superconducting is far off. It's way less. The number of, so if I can. Yes. So let me go back to a previous slide. So this is the magic angle for two-layer. So you can see that they are increasing successively. So it also actually gets easier for me to get a 5-layer superconductor to stabilize because it's a higher angle. The lesser the angle, the more the chance of an error, and it just likes to relax to 0. Yeah. So moving forward, we were able to actually characterize this MATTG into 2 different things, which is that it actually is not a plain superconductor. It is a network of Josephson junctions. And secondly, it has a competing magnetic order that competes with the superconductivity in this system. Now, initially I said that superconductors don't like magnetism or magnetic fields, but this then becomes interesting as to how a superconductivity is competing with a neighboring magnetic order. So in the first part, like Jyothishman was correctly hinting at, whenever I try to stack 3 layers of graphene, they are not perfectly rigid layers actually. They sort of try to locally arrange themselves to get into an energetically minimal state. In particular, in MATTG, it so happens that it tries to form this kind of, so we call this a lattice relaxation, and this lattice relaxation gives rise to this kind of a pattern. The colored part is basically the local twist angle in this system, and this is an STM topography result. So the scale bar is like 50 nanometer. And the devices that, like in contrast, the devices that we measure are like 1 micron cross 1 micron in size. So what happens is that we are not getting a homogeneous twist angle across our device. There exists this pattern. And this actually results in a network of Josephson junctions. Why? Because these large blue areas are closer to the magic angle, whereas the red, yellow, and the cyan areas are not. So whenever I'm off from the magic angle, it's not superconducting anymore. And basically then the structure-wise, I get something that is a superconductor, and it's separated by something that's not a superconductor, and then a superconductor again, which is essentially what a Josephson junction is. But not only do I get one Josephson junction, I get a network of these in my system, because essentially I'm probing a 1 micron cross 1 micron area, and I get multiple of these patterns in my device. So basically that's something that is actually unique to MATTG, that it relaxes in this pattern where there is large areas of superconducting magic angle-like regions, And there is this formations of these domain walls, which are called solitons, and this flower-like structure, which are actually called twistons of higher local twist angles. And they actually form these weak links in the superconductor, which gives me a network of superconductors. So that's the motivation. I did not get this by my own measurements. That's what I know previously. How do I infer this from my own measurements? Is if I look at a Josephson junction's behavior when I try to switch it from a superconducting zero voltage region to a non-zero voltage region using some DC current. When I do that, every time that I do this switching, it actually does not occur at the same exact current. This is a stochastic system where this transition or this switching happens at a different current each time you do this experiment. And why is that? You can actually visualize this switching of a Josephson junction in the form of this washboard potential. So whenever you see this particle in this potential, it is in this zero voltage superconducting part. And whenever this particle has popped out of this potential, it has gone to a non-zero voltage drop. So as I am increasing the current, what actually happens is this potential starts to tilt. And it's much more likely then for this particle to just pop out of this potential. But no system is actually without any thermal fluctuations or thermal noise. So there can be some thermal fluctuations which in some tilted state can pop this out. And that is totally stochastic. So if I do this experiment multiple times, I can actually make a histogram of the currents at which point this transition happens. So these are called the switching distribution, the histogram of the switching currents. So that is what I have studied in MATTG. So I took these individual curves of DC-IV curves for MATTG, and I sort of did this 10,000 times. I measured the switching current 10,000 times, and I made these histograms of the switching current, which then I studied as a function of temperature. How are these distributions changing with the temperature? Each histogram takes around 2 hours to acquire. Yes. Yeah. So, I mean, we've developed a technique that takes 2 hours, but if you would do this in a conventional way, but this particular data itself took like 20 minutes, one curve. So if I would take this 10,000 times, it would be much, much longer. So we actually found a way to do it faster, but still, even then, 10,000 takes 2 hours. Yeah. So then I basically plotted this distribution as a function of temperature and tried to understand what is this distribution telling me. First off, there are many things I can infer from a distribution, but I tried to look at basically this quantity, which is basically the standard deviation of each distribution normalized by the mean of the distribution. And I plotted that as a function of temperature. Now you can see two very distinct parts where one in the first part, this is more or less a constant. And in the second part, this is highly dependent on temperature. What is that telling me is that there are two regions. One is this macroscopic quantum tunneling. So think of this particle in a potential picture. You can obviously pop the particle out, but since this is a quantum mechanical system, it can also tunnel through. So unless and until I give enough temperature for this thermal fluctuations to actually affect it, it can always tunnel through. And tunneling itself is a process that is independent of temperature. So across all this region 1, you can see that this is independent mostly of temperature. And this is the tunneling part. But after a particular temperature is reached, it's much more likely that the temperature fluctuations is popping the particle out of the potential. And then it's highly dependent on temperature. As I go on to increase this temperature, which basically means that the standard deviation is much larger. For a much larger value of currents, I'm still getting a switching. It's a much wider distribution. Now, what I also studied is that if I apply some very small 50 millitesla of perpendicular magnetic field, this transition point where it switches from a tunneling dominated state to a thermally activated state, this transition point actually should come down, because it's much more likely then for it to be thermally activated. So basically, that is also what we found. And the presence of simply the presence of this tunneling and this thermal activation results in my system then tells me that this is actually not a homogeneous superconductor, but is behaving exactly like how a Josephson junction would. Because these properties you would not see in a normal superconductor. So that what we found out was indeed that this lattice relaxation is giving rise to such a system which is behaving then like a network of Josephson junctions. Now, I only analyzed one part of this distribution, which is this quantity, sigma over IS mean. There are many other quantities that I can analyze, and what I did next was look at the mean current of these distributions. So if I see these distributions and you see just visually, they are sort of going in a curve-like manner. They're not quite monotonically decreasing. So if I just look at the mean current, indeed it appears that there is a slight upturn with temperature before it falls down. Now, in conventional superconductors, as I increase the temperature, the critical current or the switching current should monotonically decrease. And this is how it should look, this green curve. But what I am getting here is now an upturn, an increase in the critical current as I am increasing the temperature. And that's pretty counterintuitive. Why is this happening? So a possible picture to sort of explain this is that there exists a competing order.
Some hundreds of micro.
Yes, around a nanoamp.
That's
That's the width of that's the standard deviation. Yes. Yes. So there exists a real upturn, and it's not just something that is because of the error. So a possible reason why we see this upturn is because there exists a competing order. Now, what is this competing order actually doing? There, in the ground state, there is a competing order and there is a superconducting order. Now, in the initial stages, when I am increasing the temperature, the superconducting order actually strengthens at the cost of this competing order weakening. That I see as an enhancement of critical current. Now, beyond this particular temperature, then, when the competition is less weak, the superconductor acts like it would have, and the critical current monotonically decreases with temperature. Temperature range. Yes.
When you have the little upturn that you get.
Yes.
It's only for
Very small.
1 Kelvin.
Yes. 0.2 Kelvin. Yes. 200 within 0 to 200 millikelvin. Very small temperature range. Yes. Yes. So we have been able to measure this on 3 independent samples. And not only that, like I told you, this superconductor is tunable. I'm not just biasing at one point. I'm able to sort of sample it by changing the doping and the electric field, different kinds of superconductors. So every time I get this upturn. Yeah. So basically then I think of that, okay, there is a superconducting order and there is a competing order. The next natural question to ask is, okay, what is this competing order? Yes. You mean this? Yes. Yes. Yeah. So actually that can be explained. If you don't mind, I can take this question at the the last of the talk so that I don't, yeah. Yeah, so the next natural question to ask is, what is this competing order? And like I told you about this Pauli limit violation and everything, magnetic field was already a very good candidate for us to probe into. So also previous literature saw effects of the superconducting diode effect, where basically positive current and negative current has different switching biases, and that actually hints to a time reversal symmetry breaking. And also these multi-terminal devices with non-reciprocal responses hinted that there exists already a magnetic order in the system. So then basically what we did was look at these histograms as a function of a temperature. So what we did was thermally cycle our system in the absence of some in-plane magnetic field and in the presence. So what you notice here is that in the absence of some magnetic field, these histograms then sort of come back on top of each other, whereas in the presence of some -1 Tesla magnetic field, they don't. And in this plot, interestingly enough, the only place where these two histograms don't fall on top of each other is 200 millikelvin, which is exactly where the upturn, the direction of the beam value changed. We also studied these histograms as a function of in-plane magnetic field at stable base 20 millikelvin temperatures. And so basically we cycled the magnetic field going from -1 to 1 Tesla and then back from 1 to -1 Tesla. What we found always to be true is that the switching histogram for 1 Tesla, which is this purple one, was always having a mean current smaller than the one which is -1 Tesla. So this tells you in some sort of way that the system is preferential to a particular direction of the magnetic field, in the sense that 1 Tesla and -1 Tesla is not equivalent to the system. So from this, you can infer that obviously something magnetic is going on in this. There is some intrinsic magnetic order that is present that is preferring a particular direction of magnetic field. To probe more into this, we tried to actually go and look not only in the superconducting part, but a little bit outside of it, where my device shows some non-zero small resistance. And we sort of got this curve, which clearly shows the presence of some hysteresis features, clearly marking that there is a magnetic order present just right outside the superconducting region. So then it's sort of natural to sort of connect the dots and say that, okay, I get signatures of magnetic order in the superconducting part and also clear signatures of magnetic order in just outside. So the superconducting order is actually competing with the magnetic order. And not only that, we also studied the presence of this hysteresis features with temperature, and it actually sort of vanishes as I increase the temperature. So that gives you a sort of a scale to compare both the superconducting order and the magnetic order. And interestingly enough, there is also the presence of this magnetoresistance, which is that the resistance of my system increases as I apply magnetic field. Now that also actually independently points to the presence of a magnetic order. But if you see carefully enough, there is the hysteresis present and there is a magnetoresistance. But when I go here, there is no hysteresis and there is also no magnetoresistance, which tells me that these two things are connected in some way. The disappearance of the hysteresis also connects to the disappearance of my magnetoresistance. Now, I also sort of tried to study this hysteresis with out-of-plane magnetic field. And indeed, you can see this hysteresis also with an out-of-plane magnetic field, but it is not quite prominent as it is with the in-plane magnetic field. So basically, these dots are just the biasing outside of the superconducting region, so the neighborhood of these superconducting regions. And I study the hysteresis of both linear as well as a transverse resistance, which shows some amount of hysteresis, but it's not very prominent, telling me that this magnetic order is perhaps more oriented towards the in-plane magnetic field, some in-plane magnetic order. Interestingly enough, I also sort of stumbled across a device which was a failed superconductor. What do I mean by a failed superconductor? It means that I got this characteristic dip that I usually see in my devices, but this dip did not go to a zero resistance, which means that it could have been a superconductor and it was not. And even in this device, when I sort of looked at the neighboring points of the regions what could have been a superconductor, I did find some amount of hysteresis present. And this particular plot does not have any hysteresis and it's at the middle, not near the superconducting part. So when I get such devices which probably has an angle off, that I did not get the superconductivity, but I still have that magnetic order. And even in this hysteresis sort of dies out with temperature, but it happens at much lower temperature. Earlier, it was dying out close to 900 millikelvin, and here, even in 500 millikelvin, the hysteresis is gone. So in that, our understanding is that this magnetic order is actually present over a larger range of twist angles in the system, but the superconductivity is more special and it's more confined to a rigid range of twist angles. Now, I would like to change the gears here because I told you about the two things that I promised you. One is that the MATTG as a network of Josephson junctions, and second is about the presence of a magnetic order that is competing with the superconducting order in the system. Now, essentially, now I would like to talk to you about the superfluid stiffness, which is an additional part of the work that we did. Now, what is superfluid stiffness? Usually in superconductors, we can define an order parameter where this is basically the superconducting gap, and the phi is actually a phase that I can define for a superconductor. Now, the superfluid stiffness is basically an estimate of a phase twist in the superconductor. There are two ways I can make a superconductor go normal. One is if I apply so much more energy through the superconductor that it's greater than delta, and then the superconductor basically switches to a normal state. For example, if I increase the temperature and the temperature energy scale is much, much larger than delta, you have crossed the critical current, the critical temperature. But I can also make it go normal if I just have many, many vortices in a type 2 superconductor. In that sense, what is happening there is I did not break this delta threshold of energy, but I just inherently included a lot of phase twist in the superconductor. Even in that sense, I am able to actually make a superconductor go to a normal state. So this superfluid stiffness actually is the energy cost required for twisting the phase in the superconductor. And that itself gives me more additional information about a superconductor than just my critical currents at critical temperatures, which give me a more direct estimate for delta. And it so happens actually that due to the inertia of the Cooper pairs, a superconductor actually behaves like an inductor. And this inductance values is actually related to the superfluid stiffness. Now, an estimate of this superfluid stiffness would give us insight about what this inductance is and also about symmetries of the order parameter. Now, usually when we look at IV curves of a superconductor, they are nonlinear. And they are nonlinear connected to this exponent alpha, which is actually surprisingly related to the superfluid stiffness. Now, there exists something in the 2D limit called the BKT transition, where this alpha actually has a jump from a value 3 to 1. And similarly, if I just put in this value back to JS, this also shows a jump. So this value, that the JS value jumps from some non-zero value to a zero value, is known as a BKT transition and is expected to be seen in 2D superconductors. Now, what we did was we measured basically different IV curves at different temperatures in order to get a handle at this alpha. And usually in this field, people did this analysis at a current which is closer to the critical current, where this nonlinearity mainly occurs because your Cooper pairs have started to depair, because you're basically sending too much current through it. But the essence of the BKT physics actually happens at a current value which is like one order lower to this critical current. And so we carefully did this analysis at lower values of current. And what we got here is these values of alpha for different temperatures. And you can see that it never quite reaches 3. And there is no sharp jump. Now, how do we explain that? This actually happens because the system is inherently disordered. This sharp jump I can actually theoretically see only in the clean limit of the system. Now, we have talked about how there is lattice relaxation and different local twist angles in the system, and that inherently makes my system disordered. So it was foolish of me to even expect that I would see this sharp jump. So there is actually no clean BKT transition happening. Nonetheless, if I apply these equations, what I can do is I can estimate the superfluid stiffness. And that's what we did. And the value of the superfluid stiffness that we get is actually much closer to later on experiments that were done, which were a direct sort of measurement of the superfluid stiffness. So as an estimate, this is not a bad way to go about this. Yeah. So with that, I would like to sort of summarize whatever I told you today, is that the MATTG we found was a network of Josephson junctions due to the presence of weak links. There is a presence of a competing magnetic order. The macroscopics of that magnetic order we don't fully understand right now, but what we can say for sure is that there exists a magnetic order. And that itself is interesting because the general sense for superconductors is that superconductivity and magnetism do not go hand in hand. This magnetic order is also actually seen in samples that do not show superconductivity, telling that the system hosts this magnetic order over a larger range of twist angles. And in a small last part, I told you how we have actually estimated the superfluid stiffness in this system. So with that, I would like to acknowledge all the people that have helped me during this project, my collaborators at Columbia, IIT Kanpur, and NIMS Japan, who have given us the HBN crystals. I thank Mandar for giving me this opportunity to present this work, and also Parag sir for giving me this platform. And with that, I end my talk.
The wonderful display of the work which you have done, and for the person who is not in the field of superconductors and things like that, it was quite useful to understand how what exactly goes through. With that, I'll open up for questioning. Audience has.
So for twisted bilayers, there is no lattice relaxation or these Josephson junctions?
Yes, so lattice relaxation happens each time you will try to put two layers of materials together. That will always happen. What is special for this MATTG is to make that particular structure with the solitons such that it forms a network of Josephson junctions.
Is accurate. The physics of relaxation will happen, and there are experiments which say that it's not a homogeneous superconductor. It is also, all of these are inhomogeneous. And people are trying to understand whether that physics comes from this relaxation. Zero thought, everybody starts that these are plates, but they're not really plates when some sides lie on top of some sides, they will kind of relax it right here. They will taller in some minutes and they will sag in one direction. So that physics of relaxation is intrinsic to these materials because they're kind of floppy membranes.
Talk about these distortions on those graphene monolayers. So graphene, of course, has been identified by the D and the G band ratios and things like that.
Yes.
Whether you have a monolayer or not, a bilayer, a trilayer.
Yes.
However, have you looked at the low frequency modes? Because these are carbon backbone, and any distortion in the benzene unit will be reflected in the intensity of the low frequency modes, which would be torsional across the across a localized pocket. So there should be some local structure that can be picked up
Yes.
by the modes at around somewhere around 100 wave numbers or lower than that. Have you attempted to look at that in your sample?
No, we have not attempted
Maybe it would be a
to look
good
at.
way to look at systematically bilayer, trilayer, and so on and so forth.
Yeah, I mean, that is an interesting suggestion. We can,
There was some localized modes.
yes. The fact that there exists a localized mode is like the colored local twist angle that I showed you is actually an STM data. So you can pick up that there is a local twist angle change even from STM, because if you have different angle structure of different atoms, they are basically a little bit different potentials. You can pick that up very accurately with STM topography. But I am not sure exactly about the details of how it would be picked up with Raman.
Hi, that was a very nice talk. Coming back to the bimodality.
Yes, I was going to come back. Yeah. So basically, you saw that at low temperatures, the histograms were single modal, unimodal. But as I increase the temperature, you saw up to 1 Kelvin, they become sort of bimodal. And what we saw even further was that if I keep on increasing the temperature, this bimodality of structure sort of spreads. And at the end, what you get is a much, much wider distribution. Now, how do I explain that? Is basically when we are increasing the temperature, this kind of superconductors are essentially type 2 superconductors. So there is influx of vortices. Now, you can imagine a state where I am at this 1 Kelvin temperature, and I have this network of Josephson junctions. Now, this vortex is present at one network, one circuit of Josephson junctions, whereas it's not in the second. That will affect how my Josephson junction switches. So in a sense, I have created two parts of my system, which will switch at two different currents, because of the presence and absence of vortices in one part versus the other. So when I am actually sampling my 1 micron structure, I am sampling both these networks, which has a vortex because of which it has a lower switching current, and a network which does not have a vortex and it has a higher switching current. So if I do this statistically enough number of times, I am sampling both. So that is actually the reason why there is a bimodality that is getting introduced. And even so, when I sort of keep on increasing the temperature, there are many, many vortices that are keep on popping in the network. Then basically you have a distribution, a very wide distribution where different strengths of vortices are making different networks turn or switch at different currents. So you have a distribution that is much, much wider. So basically to multimodal. Now you cannot actually see each mode separately because it's sort of proliferated.
Any idea as to why it is asymmetric about the median? Fusion.
Yes.
For T, from T equals to 0.8 Kelvin to T equals 1.4 Kelvin?
Yeah. Yeah. So basically these histograms are not symmetric in nature. And why that is because, remember this potential, particle in a potential picture that I was telling you about. So whenever you are tilting this particle in this potential, When I am at zero current, this potential picture is flat. There is less probability of that particle going out of the potential. But as I have tilted, there is increasing number of probability of that particle popping out. So at higher currents, actually, you will see that it is sort of more, but it has a low sort of, sorry. Oops. But it has a long tail at lower currents.
Okay. Yeah, thanks. Anybody has any other questions? You can answer.
So what I showed you just now is not a direct measurement of the superfluid stiffness. It is an estimate. Yes. So that is work done by other groups, and where basically how they do that superfluid stiffness measurement is actually by looking at this value, which is the kinetic inductance. You can make LC circuits essentially, and you can see what this L looks like by incorporating your system into that LC circuit. Very, very bluntly put.
Maybe a very naive question, but are there any observable effects if we apply a magnetic field perpendicular to the plane of the trilayer graphene system?
Yes. So basically, this particular superconductor does not like magnetic field like any other superconductor. Now, the range at which this superconductor changes to a normal state while I apply perpendicular magnetic field is much lower. It changes in some sense like till 300 millitesla or something, 0.3 Tesla. Whereas in plane field, I am able to go to much higher things. So even like I showed you, I see some sort of hysteresis even with the application of out of plane magnetic field, but they are not as prominent as I see them with in plane magnetic field.
Are there any other questions? Thanks. I have one quick question for you. You mentioned sample preparation and then having a failure rate somewhere in the video.
Yes.
So can you elaborate how many you have to go through to make one good sample where you get those readings which you showed wonderfully well?
Yeah, I mean, it is difficult to make these samples. So in a sense, what I did for this project was I made about 20 plus samples, and let's say 4 of them worked.
Each one of those samples takes you roughly about 20-25 days to progress through steps to get to the value.
Yes.
That is very nice. Thanks. Okay. Thank you very much for a wonderful talk and giving us a very good insight into this. Thanks, Akhil. I request everybody to please join for the tea and we can continue the discussion there. Thanks.
Thank you.